we have just a few times remaining, I guess. We're going to talk a little bit about sequences of functions. This is something that we started talking about last time, and I want to continue. Sequences of functions, and do they converge to some other functions? Sequences of functions. Gassing us. Here is, so simple example, how about fn of x equals something like x over n. This is always going to look like a function which has n as part of it. All right? So if I were to just write out a few of these, it would look like x1 is x over 1, which is just x, and then x over 2, x over 3, x over 4, etc. On a graph, they all look like lines, right? The first one is this. That's just x. And then x over 2 would be something like that. X over 3, something like this, etc. And I suppose if you want to draw the dots, there's some dots over there too. All right. This is just a bunch of lines, like so. Can we say, in this case, do they converge to something? Here, fn of x converges to, what would you say? Think about those lines. Does it actually become a function in the limit? Yeah? 0, yeah, I would say the horizontal line, 0, the function, not the number 0, but the function, the constant function 0. Constant function 0. All right, great. Yeah, this is a simple example. I had some less simple examples last time. I got one more sort of strange and interesting example of a sequence of functions. Here's a weird one. Each function looks like this, sort of a all zeros and then a spike and then all zeros again, where the spike, I'm not going to write a formula for this, but the spike looks like this. Sorry, not 2n, I meant n over 2 there. And it goes up to height n. I did not mean n over 2, sorry, I meant 2 over n. That's my final answer, all right? So the graph here makes a triangle, kind of. It's all zeros, and then it has that spiky thing, and then all zeros again, all right? Where the spike goes up to n, and then comes back down sort of in the horizontal direction down to 2 over n. So for instance, if I were to draw just what a few of these would look like, the first one, n equals 1, goes up to 1 and then down to 2, right? That's the first one. The next one, n equals 2, goes up to 2, but comes down to 1. So it's like this, twice as high, but also kind of twice as narrow. This is the first one, f1. This is the second one, right? It goes up to n, and then comes down to n over 2. And then the next one, f3, would go all the way up to 3, so it's even taller, but then comes down and hits the x-axis at 2/3. That's f3. So what you're getting are sort of taller and taller, increasingly tall, but also increasingly narrow spikes like that. And then the function equals 0 everywhere else. I didn't draw it that way, but out here it just equals 0. All right. These triangles, I will have you notice. Can we say what's the area of this triangle? Say this triangle right here. You remember your elementary school geometry? Did they do this in elementary school? I don't know. What is it?
1/2 the base times
Yes, it's half of the base times the height, which would be 1/2 times the base is apparently 2 over n, and the height is n, which is 1. Yeah. What's interesting here is the area there does not depend on n. Actually, these triangles, all of them have area 1. That's kind of the point of this construction. These triangles are created so that they all have the same area, 1 every time. All right. They get super narrow, but at the same time they're getting super high, and it all evens out perfectly so that they all have area 1. Okay? I would like to know, what does the functions converge to in the limit, if anything? Last time around we had some functions where kind of like the curves just sort of became vertical in the limit, and then we just said that doesn't converge to anything because a vertical line is not a real function. All right? This is different though from that. Does anybody feel like this is different? Or maybe you thought I was going to say it becomes vertical and so it's not a function. I think something's different about this one though. Yeah?
It still has to have an area, so it can never be just a line.
Yeah, like none of these functions is only a vertical part, right? Because they always come back down and then they equal 0 for the rest of the time. So as you get further and further down this list, they don't actually turn into a vertical graph. In fact, they're all. Would you agree with me if I said actually, if you look at any specific point, eventually those functions are all going to be 0 at that point, right? Because the spike gets so narrow that, say, take whatever this point is, 1/5 or something. You only have to go a few functions down before they're all going to be 0 at 1/5 because the spikes get so narrow. In fact, I believe that's true for any value of x. For any x greater than 0, when the n is big enough, fn of x will equal 0. That's because no matter how close it is to the origin, eventually those spikes are going to get even narrower than that, and then the function will just always be 0 at this point. All right? So that's true for any x more than 0. What about when x actually equals 0? Well, when x equals 0, these functions, they are all 0. That's part of their definition, is that the function is always 0 when x equals 0. All right? This is a somewhat uncomfortable conclusion then. This bunch of functions, they actually converge to 0. Even though they have this spike that kind of just doesn't go anywhere. They all converge to 0 because no matter what value you choose, any x value along here, eventually when the n is high enough, the spikes will move to the left of that value, and so that value will be 0. The y value will be 0. So our conclusion is actually fn of x converges to 0 for any x, no matter how close you are. Those spikes, they just evaporate somehow, and they become irrelevant completely. Even though for any particular n, the spike is always there, and always has area 1 under the curve. But in the limit, it approaches the constant 0. All right? So one very weird thing you can say about this is that in this case, can you believe it? I'm writing an integral sign. The rest of them are just as surprised. But in this case, if you look at the area, we're not really going to get into the integral in this class, but if you look at the area, it's always 1, right? For every one of those f's, the area of the triangle was always 1. But when you converge, or when this thing converges, well, can I just say the integral of 0, of course, is 0. So what you have here is a sequence of functions. All of the functions have area 1, but they converge to something which has area 0. This is very strange. All right, this is one of my favorite examples of a sequence of functions that converges to something in a weird way. Each of these spiky things, the individual spikes don't ever go away. They just get taller and skinnier. But in the limit, the whole thing converges to just the zero function. Yeah.
How would you write like this sequence? Like what is the function?
Well, it's this, if you like. Although apparently you don't like just this. If you wanted to write a formula for that, I would write it. I'm not fully prepared to do all the details of this because it's not really important for this example. But I would say 0 if x is less than 0, less than or equal to 0. I would say it is this line segment has slope n. Right, the rise over the run is n over 1. No, this point is 1 over n. So the slope here is n divided by 1 over n, which is n squared. So this is a line with slope n squared. Here, if x is between 0 and 1 over n. You have to write this in pieces, right? It's basically 4 line segments, so you can figure out the formulas for those if you wanted to. The next one would have slope negative n squared, and then but it doesn't go through the origin, so you'd have to figure out, like, use the point slope form or something. This is why I didn't want to get into it. And then, can I just say, that is not really hard to figure out, but I'm not into that right now. And then it's 0 again when x is more than 2 over n. And it's some other weird thing in between this range, but it's just a number, right? So you could write the formulas if you really wanted to. All right. Anyway, I'm trying to say these functions, when they converge, weird things can happen. That's the moral of this little example here. This first example, not very weird in my opinion, but this one is quite weird because you have individual functions, all of whom have some area, but they converge to as the zero function. Very strange in my opinion. All right. Anyway, this is all by way of introduction. I'm just trying to show you what sorts of things can happen with functions and what they converge to. So I want to talk specifically now about what do I really mean when I say functions converge to another function. So let's talk about convergence of sequences of functions. Convergence of sequences of functions. Just like for continuity, remember we had pointwise continuity versus uniform continuity. There are similarly 2 important types of convergence that we're going to talk about. So there is pointwise convergence and uniform convergence. And what I want to, we only have a few days left of class, but the big moral of the what I want to get across is pointwise convergence. Weird stuff can happen. Actually, the example that I just showed with the triangle thing, those functions, they do converge pointwise to 0, but the convergence is not uniform. When you have uniform convergence, it is much more nicely behaved. So when functions converge uniformly, this is basically no weird stuff happens. And by weird stuff, I mean things where the thing it converges to really looks totally different from any of the individual things. In that example with the triangles, all of the individual functions had those triangles in them, but it converged to something with no triangles at all. That was very weird. That is an example, actually, of functions which converge pointwise, but not uniformly. Uniform is a stronger type of convergence, and it turns out that if things converge uniformly, then it's much more ordinary types of examples. Like this example here, actually, in this example, it is a uniform convergence. In this example, it is not a uniform convergence. So that's a lot of the things. For instance, there are many, many theorems about uniform convergence that say things like, if all of the functions are continuous and it converges uniformly, then the resulting function is also continuous. Or if all of the functions have integral equal to 1 and it converges uniformly, then the answer function also has integral equal to 1, that kind of thing. All right. Anyway, this is where we're going. This is kind of like my main goal, to do a bunch of examples on in this general theme. So let's talk about pointwise convergence first of all. This one is very similar to stuff that we've talked about before. So let's talk about pointwise convergence. And actually, I'm going to sort of put pointwise in brackets. Usually, if I just say convergence, what I mean is pointwise convergence. All right. Uniform convergence is kind of a special kind of convergence, but the ordinary convergence, I use the word pointwise when we want to distinguish it from uniform. But if I just say convergence, I mean pointwise convergence. So here's the definition anyway. This will look very familiar. If Fn is a sequence of functions, and I'm going to say A is a subset of the domain. We say Fn converges to F on A. Fn converges to F on A means some business with the epsilons. It means, well, actually, you don't even have to really say it with the epsilons here. It means for each x in the domain, Fn of x converges to F of x. I'm not sure if it looks like I'm saying anything here. I'm trying to define what it means for a sequence of functions to converge to another function. And what it means is when you actually plug values in, those values converge to these values. All right? It kind of looks on the surface like I'm just saying the same thing again both times, but it's not. Here I'm talking about Fn as functions, and F is another function, whereas here I'm talking about once you plug a number into this function, those numbers that you get as the answers approach those numbers that you get as the answer there. All right. Anyway, this is what it means for a sequence of functions to converge to another function. Let's just do a bunch of examples. How about Fn of x equals sine of x over n? Right away breaking out the sine and the cosine, just the sine actually. This you should be fearful of in general, but actually it's not a big deal in this example. It's not all that weird. Sine of x over n, although this is kind of a weird example. If I were to draw the graph of this, for n equals 1, I get sine of x, which just looks like sine of x. Everybody loves sine of x. Goes on forever, of course. What about, so this is sine of x, right? The next one, F2, would be sine of x over 2. Anybody remember what would that look like? Another things you learn in calculus but don't use all that often. Yeah?
Is it like half the period?
Half the period or something. Yeah, this will change the period, which is to say how wide the oscillation is. It's still going to go up to 1 and down to -1, but I suppose you have two options. Is it, when you say half the period, do you mean it does that? Or do you mean it does that? The second one?
No, wrong.
I think that's wrong. I think it's the first one. Because, for example, if I plug 2 pi in when n equals 2, it's as if you were doing sine of only 1 pi. So it ends up there rather than back here. Yeah, so this, the red one here, this is, the black one, that's F1, right? The red one here is F2. the oscillations are slower. Yes?
So it's like you could fit like two sides in the big side. Like
Yeah, I would say this one, when the denominator is 2, that means that this function takes twice as long to go all the way around. Because you're dividing out the input. Yeah, so it's like that. All right, F3 would be sort of stretched out even further, right? And so on. What do they converge to, if anything? This, in my opinion, is another very weird example. Now, when I drew that F3, I'm going to change my drawings very slightly. It should, if you look at these lumps, this one looks like it doesn't make it up as high as those ones, but actually it does make it up as high. It just takes longer to get there. I don't know if that was even obvious on my picture. It still goes all the way up. It just takes longer to get there. Yes?
so by the function, like the sequence of functions converging, so like when you get to like a function really far in the sequence, like what function does it look like? Is that
Kind of, yeah. Well, kind of. It means this, really. It means this. So when I'm talking about pointwise convergence, the question I'm trying to think about is what does Fn converge to, if anything? Maybe the answer is it just doesn't converge to anything. In that case, we would say it diverges. What does Fn converge to? According to the definition of convergence of the function, it just means that when you plug the values in, they all converge to these values. So maybe it would be helpful to think about, for some x, for some sum x, I put two sums in there. For some sum x, what does Fn x converges to what, right? That's what I would like to think about. So this, we can just use the formula. It would be sine of x over n. Does that converge to anything? Don't even think of that as a function. Just think of as if x was a specific number. Any thoughts about that? What is that approach when the n goes to infinity? Any idea? Huh? Doesn't approach anything? I think actually it does. Sine of 0, yeah. This thing, if the n is allowed to go to infinity, you should feel like somehow this just becomes sine of 0. Because if x is a specific number, and you're dividing it by increasingly higher values of n, I hope that everybody believes at least that x over n really does converge to 0, right? Does that mean that I'm allowed to sort of plug each of these things inside? I'm doing some slightly weird black magic here. Can you really start with this and then like do sine on both sides? That's kind of what we're doing. Nobody was objecting until I asked the question. Are you really allowed to do that kind of a thing? The answer is yes, if the function is continuous. Because remember, that was a basic fact about continuous functions, was that if x approaches a, then f of x approaches f of a, right? This is a basic fact about continuous functions that we have talked about before. And that's really what you were doing when you said, okay, I know x over n approaches 0. That means that sine of x over n must approach sine of 0. That's because this is actually valid since sine is continuous. You can do that, but only with a continuous function. But that is a continuous function, so no problem. All right. Anyway, this is 0. All right. So actually, can I say it seems Fn, again, this approaches the 0 function. It seems like everything we talk about approaches the 0 function. That's not always true, but it has been true for all the examples. This, in my opinion, is also very weird, just because when you look at the picture, It certainly doesn't look like it's approaching 0. It looks like it's just stretching out really far. But it is still the case that every value, if you think of like, if you imagine, say, choosing this x value, are the function values eventually going to be really small, close to 0 for this one? And the answer is, well, yeah, because these eventually will stretch out so far that this value is going to be really close to 0. Strange but true. A question about it?
It still has to end with 1 and -1.
It's true. Yeah, these functions, each individual function still goes all the way up to 1 and all the way down to -1. But if you are only focused on a particular point, it is true that all of these functions eventually will look like 0 near that point, even if your point was way out here somewhere. All right? This is just a weird thing about, this again is an example of pointwise convergence, but it's not uniform convergence. So these functions, point by point, they do go to 0, even though each individual function is not approaching 0 in the ordinary sense. All right? So anyway, it seems like Fn approaches 0. Can we actually prove that? Actually, what we already wrote is basically a proof here. I just say let x be any real number, then Fn of x is sine of x over n, and this goes to 0. Again, I will just say since sine is continuous. It's really the same stuff that I wrote already, is already a proof. All right? So that means Fn of x approaches f of x, where f of x equals 0. That's what it approaches. It approaches the constant function, which is constantly equal to 0. Very strange, but not actually hard to prove. Once you realize that it's supposed to be 0, the proof is kind of very straightforward. All right. Like I said, looking at the pictures, you may be misled because the pictures don't actually seem like it's going to 0. But if you think about it point-wise, point by point, it really does go to 0. All right? I got another example. This is one that we finished off at the end last time. How about Fn of x equals e to the nx? So this one, I mentioned like in the last 5 minutes, I don't know if you recall, e to the nx. E to the x, the first one, looks like this. Everybody knows the graph of e to the x looks like that. And then we had e to the 2x is the next one. That one is steeper on the right side. Well, it's actually sort of steeper on both sides. But it still goes through 1, so it has to look like this. This is e to the 2x. E to the 3x is like that, but sort of more so. All right. So, yes?
It's sort of like, I guess I was initially confused because we were using f of like x, like for both sequences of functions and normal sequences. But is it kind of like with continuity in both cases, like you're looking at just sequences of numbers for sequences, but the only really difference is that you're looking at functions rather than numbers. Like you're still like looking at values.
Yeah. We are still, so this definition of convergence of functions is still based on individual sequences of numbers which converge to one another. Yeah, it's true. Yeah, so this individual sequence right here is a sequence which converges to 0. If you imagine the x, if you imagine this x refers to a specific number, not considering the whole function. Yeah. When you talk about uniform convergence, it is much more like talking about the whole function at once. But this pointwise is really just individual points converging to individual other points. Okay? What does this converge to, point by point? We talked about this at the very end last time, but what I ended up saying was, over here, this does not converge to anything. This diverges because values of the function over here, when I plug them in, it just gets steeper and steeper. If I plug, say whatever this is, maybe 1, I get e the first time, and then e squared, which is bigger, and then e to the third, which is even bigger. So those are going to diverge. But the value 0 always equals 1, so that converges. And anything to the left of 0 will eventually converge to 0 because these guys are getting down further and further. All right, so that's what I believe this converges to. Let's, I'm going to show that Fn converges to F, and I have to tell you what F is, where F is 0 if x is less than 0, and 1 if x equals 0. And it just doesn't equal anything for the other values. So here the domain of f is, well, I don't even say f as a function, it goes minus infinity to 0 to r. I'm telling you it's domain, right? The thing that it converges to actually doesn't have, it's not defined on all real numbers because it diverges over here. It doesn't actually make a function on that side, but on the left side it does. On the left side it goes to 0, and right in the middle it goes to that special value of 1. All right? So that is the function that this thing converges to on this particular domain. This is usually doesn't come up, but this is why I had to say this business about it converges on some set. That's the domain of the thing that it's converging to. All right. Anyway, can we show that? So I'll write little proof here, I guess. It's not that complicated though. There are really two cases that we have to consider. We have to consider, first of all, when x is less than 0, and also when x equals 0, because the thing that I'm trying to show the convergence to is different in either case. So let's do the x equals 0 case first. I think that will be a little bit easier. That's a very particular situation. So first, let's take x equals 0. All right. Then we need to show, I want to show that fn of 0 approaches f of 0, right? Because I'm choosing my x value to be 0, and so this is what we need to demonstrate. And hopefully we can do that just by plugging stuff in, right? What is fn of 0? I use the definition of fn is e to the nx, right? So this is e to the n times 0. Because fn of x is e to the n times x. So I'm plugging in 0. I get e to the n times 0. And what is that? It is 1, yeah, because this is, of course, n times 0 is 0, so this is e to the 0. And everybody knows anything to the power 0 is 1. Great. Except maybe 0 to the power 0, which is complicated. All right? And what about the other? I'm trying to show this converges to this. Now, I've shown already the left side is always 1. I'm just hoping that the right side will also always be 1, and then it'll be done, right? What is f of 0? What is f of 0? It is also 1, because this f means this, right? And so you just look here. What do I get when I plug 0 into this weird thing? You get 1. It's the second case there. So f of 0 equals 1. All right? So is it true that fn of 0 approaches f of 0? Yes. In fact, they are both always equals, right? So fn of 0 does indeed approach f of 0 because they're both equal to 1, right? All right, so that was the first part. We have to show that this holds for every x in the domain. I handled this case. Let's now talk about what happens when x is less than 0. So now consider x less than 0. All right. Again, what I want to show this time, I mean, I don't know, x is kind of a variable at this point, but I want to show that fn of x approaches f of x, right? What is fn of x? It is e to the nx And at this point, you can't really do anything to simplify that anymore, right? All I know is that x is negative, but otherwise this is just whatever it is. And then what is f of x? F is that function in two pieces. Can you say what f of x is here? It is 0. Someone's giving me the hand. 0. Yeah. Because f is that weird function in two pieces, and since x is negative, I get 0 here. All right? So what I need to demonstrate then is when x is less than 0, is it actually true that e to the nx converges to 0? When the x is negative, that really is true. Because if you think about, if I look at this and I think n is becoming infinite, actually this looks to me like it's going to be infinite. But actually when x is negative, it means really what I'm considering here is 1 over e to the nx, the positive version of x. And that actually does become 0. So the answer here is yes, e to the nx is like 1 over e to the n times, something, right? Because x is negative. So actually how you should consider this is as if it was 1 over e to the n times something. And then that part really does go to 0 as n goes to infinity, right? The x is not changing here in the limit. It's the n which is changing. The n is becoming infinite. All right, so those are our two cases. We had to consider when x is 0 and also when x is less than 0. But in either case, this thing converges to 0. All right. So e to the, well, I'll just say fn of x converges to f, maybe I'll, as functions, this converges pointwise on the interval minus infinity to 0, but not any other x values. For positive numbers, it does not converge. It does converge on those values. All right. Excellent. We got about 13 minutes remaining. I think we can start talking about uniform continuity or uniform convergence then. This, what we've done so far, pointwise convergence is usually fairly easy to prove because everything just translates into individual points. It's usually easy to prove, but also fairly weird in that you can have functions which converge to some weird thing like this, or you can have this situation where these functions all look like sine of something, but they converge to something which doesn't look like that. These ones converge to the constant function 0. All right. Uniform convergence is a lot nicer properties, but it tends to be harder to work with just because it's a somewhat more complicated concept. So let's talk about uniform convergence of functions, of course. We say, here's the definition. Fn, this one you need to break out the epsilons. Fn converges uniformly to f on some domain A when you got to do the epsilons. For all epsilon greater than 0, there exists. Now, this version of the epsilons is going to be more like the epsilon stuff for sequences, right? This is the one with the epsilon and the big N. Because I'm talking about convergence of a sequence. It is a sequence of functions, but it's still a sequence of something or other. So I'm going to say for all epsilon greater than 0, there exists big N in the natural numbers, such that for everything in this set, we have the usual thing about sequences. N greater than, the big N implies absolute value fn of x minus f of x less than epsilon. All right. This is, basically the epsilon definition of convergence of a sequence, only it's for functions. And the important thing to notice here is the ordering of these quantifiers because of the way that I ordered them, I said there exists n first, and then this n works for all x. So the same n works for every x in the domain. This is what makes this very different from pointwise convergence, all right? Pointwise convergence says just when I focus only on an individual point, the functions converge to a certain value at that specific point. But this says all together, those functions converge at all of the points, all right? This is a much stronger kind of thing to say. So if it converges pointwise, it does not mean that it converges uniformly. It's a lot more to say it converges uniformly, because it means this same n works for all the x's, all right? I got just one example, and then I think that'll do us for today, of something which does converge uniformly on a certain domain. Just like uniform convergence, the domain is very important. I want to talk about f n of x is 1 over n times x. All right. Let's, I'll try and draw this. Let's just draw it for the positive values of x, because actually the convergence here will not be uniform for all x. It's only on a certain domain that it's uniform. Anyway, when n is 1, it's just 1 over x. Everybody loves 1 over x. Looks like that, right? When n is 2, it's 1 over 2x. Another way of thinking of that is it's 1 over x times a half. Right? You are multiplying an extra 2 in the denominator. This is 1 over x. 1 over 2x is the same thing, but sort of crunched down halfway. It's the same as if I were to multiply by the constant 1/2, which just cuts every y value in half. 1 over 3x is, again, crunched it down a little bit more, right? Etc. Crunched. Yo, crunch. Remember that stuff? Yeah. Classic. Yeah. All right. I'll think about yo, crunch now. Does this thing actually converge to something uniformly? Now, I can say point by point it does converge to the 0 function, because even no matter how close you are to the axis here, at this point, eventually all of these lines will get so crunched that the function values will be close to 0 here. All right, but near this axis, I feel like they're not all going to be crunched. It's just if I look only at a particular point, yeah, eventually these functions will crunch down to 0 near that point. But if I'm considering all of the points on this interval here, they're not all going to be crunchy near the origin. So it turns out actually this does not converge uniformly on the interval 0 to infinity. It does converge pointwise, but not uniformly. And it has to do with the fact over here, it's actually kind of like uniform continuity is messed up when the slopes become infinite. And that, if you think about it, is also what's happening here. As you get further and further down the sequence, these functions, their slopes are increasing every time, right? It gets steeper every time in order to crunch down. And that's what messes up the uniform convergence if you go all the way to 0. But if you go only so far over, then it does converge uniformly on any other interval, just not going all the way to 0. When you pick up this asymptote, everything gets messed up. But if I don't go that far, let's just go to say, I'm going to say it does converge uniformly on, let's just go to 1 to infinity. Then it really does converge uniformly. That on my picture would be, say, something like here. Before we do the proof, actually the proof is not really hard, but it's just a standard sort of bunch of epsilons kind of proof. But I want to just draw this picture again to demonstrate kind of what it looks like these curves look like this, right? If I'm only looking right there, they look, oh, sorry, they look sort of like that. And what the definition of uniform continuity means is that sort of for any, no matter what little epsilon you choose, here they converge to 0, right? So I imagine a little sort of epsilon neighborhood around 0, which makes kind of a window here. And it is true that eventually when the n is high enough, the entire graph of the function lies inside this window. Only, if I only consider to the right of 1. Those red lines, eventually the entire red line will be inside that band. No matter how narrow the band is, you might have to go further down. So uniform convergence, this is like the picture you should have in your mind for uniform convergence. Uniform convergence means that eventually the entire function, by which I mean the red line, the graph of the function, lies inside the epsilon sort of strip, if you will. And that is true on this picture, all right? But it's not true if I tried to go all the way to the asymptote, then it's not true, because every one of these red lines, if you continue them to the left, they do eventually leave this strip. They go up, which is why they don't converge uniformly all the way on this entire interval here. But beyond this point, they do converge uniformly. Yeah.
So that's like the entire piece inside.
Yeah, the whole line. Yeah. Although only when I'm considering this domain, right? Yep. In 3 minutes, can we do the epsilons thing? The proof of this is really very easy once you know what you're talking about. Let's see if we can do this. So I say, let epsilon greater than 0 be given. And then we'll find n, a natural number, such that for all x in the domain, that is 1 to infinity, n greater than the big N implies absolute value fn of x minus f of x less than epsilon. All right, can we fill in the blanks? So you're going to do this just like every other epsilon's proof you've ever done.